So in front of us here we have got a Schneider Type A Acti9 distribution board consumer unit. This is typically what you would find in a commercial installation, and the reason for that is generally to do with the higher prospective fault currents you'll be expecting to see at locations where the distribution equipment is needed. So as we know, with our consumer units typically used in domestic environments, they're not really rated in a way that would be suitable for a large majority of commercial and industrial installations. I don't want to get into the thick of that at the moment. I just really wanted to talk about some of the key features of this particular board, and you will note that there are the big lugs along here. So these are a pre-installed buzz bar, if you like, for the live terminals. You will also see here that there's been a main switch installed, and note the N on there for the neutral, and we have the L for the line. Now there is also an earth bar over here and a neutral bar up here as well. But the beauty of these is you can actually use an RCBO that would clip in to this system to provide its connection to both earth and neutral. And if you see in here, you've got the little holes, and this hole there is where the earth pin on the back of an RCBO connects, and in here this is where the neutral would clamp around and effectively join into the neutral here. So you have in essence you have a line, a CPC and a neutral buzz bar, if you like, clip in clip out system, and I'll show you how that works in a minute. And obviously you do also need your usual bars to connect conductors into. So as you can see up here with the neutral one, if you imagine this was just an MCCB, for example, you know, they don't have a neutral connection built into the overcurrent protected device, so you would still need to wire away as normal. Likewise for your CPCs as well, they still need a point of termination within the enclosure itself. So it is actually quite clever how this works, and I have got an RCBO here, so I will drop it into shot now. And if you see on the back of it, position it in a way that helps make sense. There's the yellow tab here, which is what you use to release the RCBO, and I'll show you that in a second. But if you look on the back there is the prongs, that's for the neutral connection, and then this little pin here, which is for the CPC/air. If I spin it around, it actually shows those markings on the actual device itself, so you can see there the earth symbol, and then you've got your neutral symbol there as well. Now these boards are quite safe, or as safe as you can perhaps expect them to be. So when there is no RCBO or MCB connected onto these actually do isolate. So even if this is in the on position, these will not be energized because of this tab here. So if I demonstrate this being installed, if I can actually do it on camera, you see that locks under the brown tab there, so it's pushed underneath it, and then you simply clip it down, and that's it, locked in. And then you've got your yellow tab on the end, which you push into position, and that's it now clamped. Now obviously you would tighten down this terminal here, so you've got an effective connection onto the line buzz bar, and then obviously your final circuits would be wired into the neutral and the line on the outgoing side of the RCBO. Now if you don't move this tab out, you see that covers the actual screw terminal on the bottom of the RCBO. That essentially switches this on, so it allows the connection to be made into the live bus bar. And again, obviously if you need to remove the RCBO, so it's faulty or you're changing the overcurrent protected device or whatever, this tab pushes back in first, and that would release access. Whoop, knocking everything all over. That would release access to the screw terminal to undo it. Obviously this would be fixed to a wall, so it's not going to be spinning around. And then equally, if you pop the yellow tab back out on the bottom, and then it simply pulls out, up and away, and then you can drop in whatever you need to. So I like that. I think that's a pretty safe way of connecting in equipment, because you have got the isolation, if you like, of the buzz bar itself for somebody who's maybe working inside the enclosure, and you're not in a position to isolate the incoming feed onto the main switch itself. You can disconnect and open up that main incoming switch. You can even go to the trouble of locking it off, but there's always the possibility of a mistake. If that was to happen, at least if these are exposed and these tabs are in, you know that they're not going to cause you an issue. And equally, if you try and actually push them out where there's no MCB locked in, they won't move. So it actually needs that MCB or RCBO to be in place. So I can demonstrate it on this one here. Again, underneath the brown tab, lock that down, yellow tab locked in, and then it will actually open up and cover over the terminal. Get that back into shot. So I thought that was quite nice just to run through this. So this is a Type A Acti9P type board. You can mess around in the TPN version of this, where you can drop modules in and out, change the way that these are configured. Obviously with AFDDs and such as well, when you're putting them inside bigger enclosures, you know, it can all be plug and play. So I thought we'd just run through some of the instructions that come with this, and you'll see here it's an Isobar P Type A distribution board, consumer unit, whatever you want to call it, and it tells you the measurements for marking out your holes and ensuring that the level. It goes through installing the main switch, so you can see there that that actually clips straight onto the line, and the neutral pins, so that actually has a pin underneath it, which the neutral obviously terminates onto, and then, you know, see it going in there. It also gives you a bit of information about how you would remove and install these breakers. So as I showed you with the little yellow tag, you can see that over here. Same there, locking it in, and yeah, it explains to you about the cover over the MCB or RCBO screw terminal, so you can see that there. Again, if you swing out to the next page, I think it gives you some more pictures of that. So yeah, that's, drop that down a little bit, you can see that there, just at the top where it's explaining about the lock for energizing that particular way on the board. It's all quite interesting. You know, it is good, you can cover up your neutral bars. They come with all these in the boards, so they're trying to make it so there's no exposed terminals or bits of metal or copper, brass, whatever inside the enclosure itself. So in the event it is open while it's energized, the risk is as low as possible, which helps us as installers and people carrying out maintenance endlessly. That gives you a bit of a typical layout of how you might go along on the layout inside the enclosure itself. So I thought that was interesting, and again, this is for the RCBO. Basically just running through the locking in and out process, the torque values, so you can see it's 3.5 Newton meters on that particular terminal. Yeah, it's interesting stuff. Hope you found that useful, just having a little look through this Schneider Isobar P board and actually physically putting in an RCBO and then being able to remove it, and some of the safety features and benefits of this particular product. I'll drop links into the description of the video where you can go off and have a little look at it yourself, and we're going to take this out onto site on a job very soon, install it and show you what it looks like out in use, and then some of the key benefits while we work through testing it as well, because I think that's an important aspect to all this. You can have increased measures of safety while you're carrying out future maintenance if you install the right product at the outset. Okay, so I thought in this one we'd take a little look at a Schneider Electric MCCB. In this case we have a 200 amp module, so this is what you would typically find in a panel board to then feed into a sub-circuit to another distribution board, for example. And it was just to explain some of the different settings and dials on these, because I've had a few questions from apprentices who just aren't sure. I thought it'd be quite nice to run through. You'll see on this particular model you've got IR down here and a little adjustable dial with a scale from 200 down to 140, and you know it's talking about amps because you've got an A underneath there as a clue, and then we've got IM over here, and again we're going 2000 down to 1200, and again it's set as an amp value. And it's just to try and explain a little bit about those and also how these are connected together. So typically you would be fitting lugs onto your cables that are terminated onto these, usually due to the size of them. You can still get cage clamps on your MCCBs where you would wire in the cable directly without a lug, but usually that's what you find, and you have your bolts and your washers over there to enable you to do that. You've also got these little cable trays here, so the cables run through inside here, just to give a little bit of further protection again inside the distribution panel board, so you're protecting yourself. Just to talk a little bit about these dials then, and then we'll go through some of the unique features of the Schneider product. So in essence, your IR is talking about the thermal overload protection, and you'll see here its scale is sort of from 200 down to 140, and it's called the long time pickup current setting or the thermal setting, and it's usually to do with how you want that to operate in terms of an overload in essence. So you can adjust this down to 160 amps if you wish, 140 amps, and then it would operate at a lower overload current than if you were to have it just set to the maximum 200. And some of these gauges are different, so in this case it is actually numbered. Sometimes they have multipliers of times 0.8, for example, 0.6, where you can drop down the rating of the actual MCCB by using that dial. Now the IM is the magnetic side of things, so that's looking at the short time magnetic setting. So this is a multiplier of the IR setting. It's often set between 1.5 to 10 times the value, and again you'll see here that we don't have that on this scale. It's actually specifically stating a value. So if you were setting it to 2000, for example, that would be the instantaneous magnetic effect of the MCCB, where if you had a dead short, for example, it's going to allow a faster or slower operation based on how you set this dial. And again, you can have them where there's time delayed sections on these as well, so you can offset the effect of the tripping characteristics of the device if it was to need a time delay on there as well. There is loads and loads of information to read up on these. I can't explain it on a quick little YouTube video. It's just to give an overview of the dials you'll find on the bottom of these can actually affect the way that the MCCB operates as you've installed it. It's not like when you go and get a normal MCB, for example, and drop it in a board. It's rated for how it's rated. You've got the tripping curves and characteristics in the wiring regs. With these, they are manufacturer specific. You'll have to refer to their literature for the maximum earth loop impedances and their short circuit ratings, and then actually setting them up as well. There is different ways for the different products of how you do it, and likewise again bolting them into the board. We'll have a little look at the instruction sheet for this because I've got one to hand, so we can talk about that as well. You'll note on here there's a QR code, so you can scan that and it'll take you to all the product literature as well that Schneider provide. Their website is really, really good. It is full of lots of useful information. You'll see here that the EN number for this is a 60947-2, so that's your MCCB, and again you've got your product code on here and the actual rating and application of the device here, and that's actually showing you there. I missed that out of the corner of my eye, the little graph where you've got your IR and your IM. So you've essentially got your overload, short circuit, thermal and magnetic effects of the MCCB. And I'll try and find some decent articles on this and link them in with a video, because there is a lot smarter people than me who can tell you how these actually operate and how you would set them up. But again, we've got an install coming soon. We're going to be out on site installing a few of these, and I can show you us doing that. I'm going to go and grab the instruction manual now, and then we'll have a little chat through that as well. So yeah, just to see here again, you've got your explanations of what the IR and IM are doing and how those dials are moved and adjusted, and the little graphs on here. I will try and get something that I can maybe pop into this video and talk about it in a bit more detail. It explains how the MCCB can be taken apart and adjusted, so you can see all that there, what to do when it's tripped, that you actually have to push it to trip on the test button here when you're wanting to operate it and check that it's working, and you'll hear an almighty clack when it does it. It even gives you a little shoutier clacks sign. And again, you can reset them where you have to actually physically move it all the way into the off position before you can restore power. So that's that aspect of the instructions. There is this other great big sheet as well which explains how you can put the cage clamp in that I discussed earlier on in the video, or how you can just use your cable lugs to affect your terminations as well. So this is more the physical putting it together. Yeah, it's interesting, and I think that there is a picture here which shows the cable section I was talking about. Yeah, it does. So if I turn that around there, you can see here how the tunnels, tubes, whatever you want to call it, sit over the cable entry points and give you a bit of protection on that as well. You can also get these dividers as well that sit between the phases if you wish, or shield the outer edges and rear of the MCCB as well. So there's all sorts of things you can do. Knowing that this stuff's available is powerful for us as installers, so I just wanted to share that on this little video. I'm going to go and have a little dig around now and see if I can find some better explanations of these that we can maybe look at and talk about, because I realise that, you know, primarily my audience is at an apprentice level, and I'd like to give you a bit more explanation if I can. So we'll jump on with the video and see if we can have a little chat about that. Okay, so I found this helpful article on the internet. It's produced by a professional electrician in Napier. It's an old one from 2017, but I thought that this explained what I was trying to say really well. So it was written by Bill Allen from Napier, and in essence he's going through the operation of moulded case circuit breakers, so MCCBs, and explaining again how they meet 60947-2. And installers are commonly advised to refer to the manufacturer's data for your earth fault loop impedance values. Sometimes these can be daunting, so this actual article is aimed at showing you in how you can calculate what the maximum ZS would be, and I'll jump to that in a minute. But I was more wanting to focus on the explanations of how these actually operate. So it says here the topic of MCCBs is a large and complex one, not least because of the variety of types available. As with other circuit breakers, specification items such as rated current, IN, ultimate breaking capacity, ICU, and rated making capacity are all important, but space dictates that they are beyond the scope of this article. So yeah, I totally agree with that. I can see exactly why he said that. In this instance, I will also ignore electronic and microprocessor-based MCCBs. So you can do that as well. You can have logic involved in the way that these can be programmed and set up as well. So this is looking at the traditional dial types. So they want to give an introduction of how thermal magnetic MCCBs operate and explain how the maximum ZS values can be determined. So if we look at the moulded case circuit breakers, it's saying here that the actual BS number is a part of the standards for the low voltage electrical switchgear, which applies to circuit breakers and their associated units. This contains annexes of specific circuit breaker functions. For example, Annex L concerns circuit breakers without overcurrent protection. MCCBs are electromechanical devices which protect circuits from overload and fault short circuit currents. They are often preferred to your HBC fuses as they do not require replacements when an overcurrent is detected, and they can be easily reset. Some types of thermal magnetic MCCBs are adjustable thermal or magnetic trip mechanisms, or both, which ensure optimum protection and coordination of devices. And that's kind of, you know, where the application of these comes from. So as I said, if you have these in a main panel board, you will have sub-distribution boards as well. So when you're talking about selectivity and things like that, as you're stepping down through the sequence of your distribution circuits and your final circuits, being able to have some effect on the characteristics of the upfront protected device is really useful, certainly from a design point of view and from an installation point of view. And obviously those can change at times as well, so the fact that the adjustment is on there is quite helpful, I think. So it says here the operation of MCCBs, like circuit breakers, so your 60898s and your RCBOs 61009, thermal magnetic MCBs are automatic switching devices with two modes of operation, thermal and magnetic. The thermal operation has an inverse characteristic and provides overload protection, which we spoke about earlier on in the video, and high levels of overcurrent such as short circuit current. A magnetic trip coil energizes and disconnects the circuit instantaneously with no intentional delay. And then it tells you about the adjustable thermal operation, as I spoke about earlier on, and basically you have that adjustment typically from 63% to 100%. So on that 200 amp example I had, we could drop down to 140 amps for the overload, so the thermal aspect of it, and we could leave it set to the maximum rating for the actual MCCB itself at 200 amps. And then the adjustable magnetic operation, so some MCCBs permit the instantaneous disconnection time to be varied. Commonly this is a magnetic setting known as IM, and it can be varied from 5 to 20 times the nominal current. There's some variation between manufacturers on both settings, and that's important to note. It's different in the way that they're labelled on the actual dials. Some of them use a percentage, some of them use the actual values, and again you can set them based on what you want the instantaneous tripping characteristics to be. Smaller MCCBs, those up to around 160 amp, may have thermal adjustment only with the magnetic operation fixed, and larger types would normally have adjustment on both. Then it talks about the magnetic tolerance. A tolerance is included with the magnetic current value, and the standard tolerance is plus or minus 20%. Explains a little bit about the categories, and again that's on when you're selecting your equipment to be installed. Category A has no intentional time delay. Category B does have time delay facility provided on the actual device. Then it explains how you can calculate the value of ZS. Basically you would do that as it explains here, so it's using an MCCB rating of 32 amps. It's looking at the UO value of 230 volts. The magnetic adjustment is set to times 20, and the magnetic tolerance is plus or minus 20%. So it's required to disconnect within 0.4 seconds, calculating earth loop impedance value maximum for that particular product. It shows you on the graph, which should look familiar from the wiring regs. And it says here the 0.45 disconnection is shown, although the device actually disconnects instantaneously, i.e. around 0.01 seconds. So they've marked that, plotted it on the graph. And it shows you here how to work that out using regulation 414.11.4.5, and again that's perhaps changed because this will be based on an older version of the regulations. But it shows you how to do that calculation. It is basically just transposing formula, so you end up with your 640 amps, so 20 times the 32 amp rating of the MCCB. Then you've got your 20% tolerance to add on to that, so 128, and you come to the figure of 768 amps. So if you take your voltage, times it by the Cmin, and then divide it by that figure, you get your maximum value of earth loop impedance for that setup on the product. I always use the data sheets. I don't find them that complicated, but you know, if you're wanting to cross-reference and know how they come to these figures, this article explains it pretty well actually, so I will link it in the description to this video. I hope that's proved of some use. I realise that this is mainly aimed towards apprentices because again, this primarily comes from the discussion me and Neil had a while ago about derating normal circuit breakers and their use in outside locations or colder environments, for example. And we got on to talking about MCCBs, and it turns out a lot of apprentices didn't know what they were, so I had a few questions, what actually are these things? And I thought I'd do a little video just to share that and explain a little bit about what they are, where you might find them used and how they're set up. And again, it really is, when you're talking about distribution circuits to other distribution boards on large installations, you really don't want to be stacking up typical circuit breakers, so your MCBs in series, because getting selectivity between them is really, really difficult. Even when you're using MCCBs, you will often only achieve partial selectivity, but it's a lot better. And again, you can use fuses as well, which usually give you better selectivity, but the issue is if you have a fuse go out, it involves an electrician having to come and then replace that fuse and restore power to the circuit, whereas with an MCB or an MCCB, you know, within reason, that can be user controlled as long as they have some knowledge of the electrical system. You know, they're not exposing themselves to any large parts. Although I would always say, if you've had an operation of a protective device, you should really be consulting the opinion of an electrician before you turn that circuit back on. And yeah, that was sort of it really. And oh yeah, that was the other one as well. So I referenced a video a while ago now. 3-phase meter had exploded, and we'd had the operation of an upfront MCCB in a panel board, which was at the sort of main intake cupboard for a row of industrial units, and then also at the affected unit itself. It had another sub MCCB sort of in series with that one. They both operated, and then again in the actual unit itself there was an MCCB used as the main switch, and that had operated as well, and it was to do with transient voltage taking out a phase, which obviously upset everything, and all bets were off as to what would trip when and how, and the meter decided to spew its guts out and probably took the MCCBs with it. So you know, that's just a demonstration that selectivity isn't always possible when you have a really serious short circuit fault. And I'll reference the link to that video somewhere at the top of here, so you can go off and check it out if you want. I can't exactly remember what happened, so I'm maybe just waffling about that. But I hope that proved useful. If you have any questions, drop them in the comments. I'm happy to try and explain them as best I can. I'll link you on to some other information to try and take you through it. Ask your lecturers as well, ask your employers. That's one thing that a lot of apprentices seem really stuck on. It's asking for help and advice. Don't be shy. Lots of people out there will want to help you, certainly in the college environment and in your specific employers. They should be there to help you learn this stuff. So ask the questions, get the knowledge and information into your minds, and keep on pushing forward in your training. I'll catch you on the next video. Thank you very much for watching.